Hi everybody, welcome back. This is our first video of our new unit, the periodic table. So, the plan for this video is to cover the history of the periodic table and kind of look at where it was in the past and how it got to what we know and love today. And again, why it's organized the way it is. So, I want you to look at this picture quickly. So, this is funny, but it also has some, benefit to it. The periodic table of iPad apps. What do you notice about how it's organized? Is everything just put randomly there? Or is there some kind of method to where things are located? So if you look at it, you have this different key. So depending on the color of the background, that tells you, something a little bit about the element. So anything in this red with this red background is an Apple app. Anything, with that green background, anything over here, is deemed as productivity. So depending on the app's function, it's placed somewhere specifically on the periodic table. Okay, so if we're going to look at this, it'd be time travel all the way back to 1829. This guy right here, J.W. Dolbenreiner, was studying elements. So what he discovered, what he did, he organized elements into groups of three. So if we look at the word triad, tri means three. So he's organizing these elements in these groups of three. And so based on their similar properties. Oh, these three elements kind of, act similarly. Let's group them together. And so one of his most famous ones was chlorine, bromine, and iodine. So what I want you guys to do is go find them on the periodic table and tell me where they are located in reference to each other. Okay, so you should have, here's your, your periodic table. Super accurate drawing. Chlorine is right there. Bromine is right there. And iodine is right there. They're all in the same column, or we call columns groups. So they're all in that group 17. And so what you notice is that all of these elements reacted very, very, very easily with metals. So we're going to talk about how we know these are metals and how they're not. So there's this staircase that you'll see, kind of a bone line. And again, we're going to speak about this later, but anything on this side of the staircase were metals. So what they noticed is that these things, and group 17, which we'll learn in the next video, are called halogens. They react with metals. And if you think about that, you already kind of know this, because sodium, Na, is a metal over here. And you know Na and Cl give you salt. So that's kind of where we're headed. But one of the problems with this model was that not every element could be grouped into these triads, or again, these groups of three. Some of them could, but not all of them. So this shows a few triads that he had: the lithium, sodium, potassium. He noticed that calcium, which is Ca, strontium, which is Sr, barium, which is Ba, he grouped them together. So lithium is Li, sodium is Na, potassium is K. He noticed chlorine, bromine, and iodine were very similar. And then, the symbols are right there. The sulfur, selenium, and tellurium were also all grouped together. So what do all of these groups have in common? So you should have said all of these groups, or these triads, are all within the same group. So all of these are in the same group, meaning the same column. All of these are in the same group or the same column. Same with these, same with those. Okay, so let's fast forward a few more years. Now it's 1869, and Dmitri Mendeleev comes into play. So he is this Russian chemist and teacher, and he published a table of these elements. And so what he did, he showed a relationship between over 60 different elements. So that's a big step up from what Dolbenreiner was doing. So now, Mendeleev has so many more elements. And what he did, he organized them by atomic mass. Now, do you see a problem with this? Can we accurately organize elements by atomic mass? What do you think? So if you were thinking, maybe there's a problem here, because remember, we talked about isotopes. And isotopes are the same element, but they have a different mass. So you can't organize them by mass because that doesn't work because isotopes exist. But at this point, he wasn't really aware of that, so he organized them by mass. But that's why we don't use his method today. But here's a copy of the Mendeleev periodic table. So it's organized a little bit, and you can see all of these numbers are the atomic masses of these elements. Again, that looks closer to what we know and love today, but we're not quite there yet. Okay, so fast forward again, now it's 1931, and we are in Britain, and now we're talking about this dude named Henry Mosley. So, what Henry Mosley discovered was that each element had a specific number of protons. And again, this is stuff we already know, but this is how we got there. So remember, the protons is the same as the atomic number, and that's the ID of the element. So he's like, oh, each element has a different number of protons. That's what makes them different. So that is what we need to organize them by. And, if we look at this and we look at what Mendeleev had said, Mendeleev wasn't totally sure about what atoms were looking like, what the structure of the atom looked like. So Mendeleev was able to do this all without really knowing what the atom looks like. But now, if we kind of superimpose the timeline of atomic history and periodic table development, now when we're talking about Henry Mosley, we have the structure of the atom kind of down pat. We know what things are to a much better idea, or much better extent, rather. So the fact that Mendeleev was able to do this, and Dobenreiner was able to do this without knowing what the atom looks like, really, is super incredible. So if we're looking at the history periodic table in present day, the periodic table is organized by increasing atomic number. Again, that is the number of protons. And so we can look at the periodic table and look at the rows or the columns. So we call these rows periods. So, and then each period represents a principal energy level, and we're really gonna talk about what those energy levels are. But again, that's kind of bringing in the idea of what Bohr was saying. And so one of the ways I like to memorize or remember this, if you're thinking about a sentence, so someone's writing a sentence, blah 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 blah, it ends in a period. So when you're writing a sentence, you're going left to right. You're going horizontally. So just like a period ends in a sentence, in English or literally most languages, if you're writing, it's a straight line going horizontally, ending with a period. So a period on the periodic table is that horizontal row. Now, the groups and families, those are your columns. So each column has a number. So column 1, column 2, column 3, and that represents its group or family. So the first column would be group 1, second column is group 2, on and on and on. So question for you, what group is sulfur or S in? Okay, so S is in group 16, so that's the 16th column. Another thing to point out is valence electrons, and these are going to be our best friends when we talk about bonding. And valence electrons are the outermost electrons, so this piece right here. So if we look at the electron configurations, the number, dash number, dash number, dash number, that changes, and those are the most important electrons when we're talking about bonding. So if you wanted to figure out how many valence electrons somebody has, that is the last number of these electrons. So if you look at calcium, how many valence electrons does calcium have? So what's that last number in the electron configuration? So calcium is 2-8-8-2. That last number is 2, so those are your valence electrons. And if you even look closer, everything in group 2, so everything in that second column, all of those elements have the same number of valence electrons. If you look at group 16, so go all the way to the right-hand side, everything in that 16th column, all of those have 6 electrons in that valence electron spot. So for groups 1, 2, 13, 14, 15, 16, 17, and 18, that tells you the number of valence electrons. Now that middle lower section, we call those transition metals. So if this is your periodic table. This section right here, those are your transition metals. Those things get a little funky over there. So that trick doesn't really work. But that's something to look into. Now, everything I told you was a lie. This is exactly how the periodic table was made. It's a, fancy game of Tetris. I'm kidding. It's not a fancy game of Tetris. So everything really is organized by increasing atomic number. So that is the most important thing that you should have gotten out of this video. The periodic table is organized by increasing atomic number. Again, the atomic number is the same thing as the number of protons. Each element has their own specific number of protons, and that's what makes that element that element. Okay, so that's it. On the next video, we're going to talk about the different parts of the periodic table and kind of take a deeper look into each of the different groups. We'll color code it. We'll talk about what makes elements different and the different properties each of these things have. Bye.